Welcome to HVAC Master Training. In this video, we're diving into Chapter 1 of the ASHRAE Handbook, HVAC Systems and Equipment. This chapter is called HVAC System Analysis and Selection. It's one of the most important sections for every design engineer because it explains how to choose the right HVAC system, not just based on equipment, but on performance, comfort, cost, and sustainability. An HVAC system's main purpose is simple: to maintain desired environmental conditions inside a space. But achieving that involves balancing many variables: temperature, humidity, air quality, energy efficiency, and long-term maintenance. As a design engineer, your job is to analyze different system options, evaluate their impact on comfort and cost, and select the one that best fits the owner's goals and the building's design intent. ASHRAE Standard 55 defines the comfort conditions we must achieve: proper heating, cooling, and ventilation levels for occupants. When selecting a system, we must also consider factors like temperature, humidity, air movement, indoor and outdoor air quality, acoustics, and even the building's local climate. Every project starts with a conversation between the owner and the design engineer. The owner focuses on goals like first cost, operating cost, flexibility, and sustainability. Meanwhile, the engineer ensures technical feasibility, energy performance, and occupant comfort. Sometimes owners have additional goals, for example, achieving LEED certification, improving property value, reducing operating costs, or simply creating a healthier indoor environment. It's the engineer's responsibility to translate those goals into measurable design criteria and document them early in the system selection process. The ASHRAE Handbook outlines a clear, structured process for system selection. It starts with data collection, where we gather information about the building program, loads, and constraints. Then comes data analysis, where we evaluate feasible system types. Next is solution planning, which includes cost, efficiency, and performance comparisons. Finally, we prepare a recommendation report that presents the optimal system options. Projects usually follow one of 5 delivery methods: performance contracting, design bid build, integrated design, or construction management. No matter which path you take, the goal remains the same: selecting a system that achieves comfort, control, efficiency, and reliability within budget. System selection isn't just about efficiency or comfort, it's also about constraints. We have to account for performance limits such as temperature, humidity, and pressure, energy budget and available utility service, space limitations and building architecture, operator experience and maintenance access, construction schedule and delivery lead time. Constructability is key. For example, if a large air handler can't fit through a doorway or elevator, that's a design failure. Early collaboration with the builder can prevent these issues and ensure the selected system is practical and cost-effective. To make system comparisons transparent, ASHRAE recommends using an HVAC system selection matrix. Each potential system is scored from 0 to 10 based on key criteria like comfort, cost, controllability, sustainability, and reliability. This analytical approach allows the engineer and owner to clearly see trade-offs between first cost, life cycle cost, and long-term performance. In the end, the system with the highest total score, and that meets all project constraints, becomes the recommended design solution. Next, let's talk about one of the most fundamental choices in HVAC design. Should you use a decentralized system or a centralized system? Decentralized systems distribute equipment throughout the building, like rooftop units, fan coil units, or heat pumps. They offer flexibility, local control, and redundancy, but usually have higher maintenance needs and less precise humidity control. Centralized systems, on the other hand, use a central plant, such as chillers, boilers, and pumps, serving multiple zones through distribution piping. They're more efficient, provide better humidity control, and are ideal for large buildings, though they come with higher first cost and complexity. Let's break down the main categories of HVAC equipment. Refrigeration equipment includes chillers, condensers, and cooling towers that handle heat removal. Heating equipment covers boilers, heat pumps, and other systems that supply hot water or steam. Air delivery equipment includes packaged or custom-built air handling units that distribute conditioned air through the building. Some modern systems also use combined heat and power or thermal energy storage to improve efficiency and reduce operating costs. Mechanical and electrical rooms typically take up about 4 to 9% of a building's total floor area. They should be centrally located to minimize duct and piping runs, and designed with enough ceiling height for access and maintenance. Fan rooms, cooling towers, and refrigeration plants must be located where airflow, drainage, and noise can be properly managed. In high-rise buildings, multiple mechanical rooms may be placed on different levels to reduce vertical duct and pipe runs. Good design ensures these spaces are safe, accessible, and easy to maintain throughout the building's life. In multi-story buildings, vertical shafts are critical for supply, return, and exhaust air. They must meet fire separation, acoustic, and pressure drop requirements. Rooftop systems are common for smaller buildings and can save indoor space, but they face weather exposure and maintenance challenges. Air distribution systems should deliver air quietly, evenly, and efficiently. Proper duct sizing and layout are essential for minimizing noise, pressure loss, and energy waste. Air terminals like registers, diffusers, and VAV boxes ensure precise zone control and occupant comfort. HVAC systems play a major role in building security and health protection. Designers must consider threats like chemical, biological, or radiological contaminants. High-risk buildings, such as airports, hospitals, or government facilities, require advanced filtration like MARV 14 to HEPA filters and isolated ventilation systems for sensitive zones. Air intakes must be placed away from potential contamination sources, such as loading docks or streets. In critical areas, negative pressurization can prevent hazardous air from spreading to occupied spaces. Modern HVAC systems rely on direct digital controls, or DDC, integrated with a building management system, the BMS. These controls manage temperature, humidity, and air quality automatically while optimizing energy use. Protocols like BACnet and LawnWorks ensure compatibility between sensors, valves, and actuators. Smart BMS allows real-time monitoring, scheduling, and trend analysis, even from a mobile device. Effective control systems improve efficiency, extend equipment life, and reduce human error. Maintenance management is just as critical as system design. ASHRAE recommends using computerized maintenance management systems, or CMMS, to track service history, equipment performance, and spare parts. These systems can also integrate with Building Information Modeling, or BIM, for digital documentation. Proper maintenance planning during design ensures safety, longevity, and sustainability. Commissioning, meanwhile, ensures the system operates exactly as intended. It begins during design, continues through construction, and extends into occupancy. Following ASHRAE Guideline 1.1 and Standard 202, commissioning verifies performance, comfort, and energy efficiency before handover. Chapter 1 of the ASHRAE Handbook teaches us that HVAC system selection is not about picking a piece of equipment. It's about creating a balanced solution that meets comfort, cost, and sustainability goals throughout a building's lifetime. By integrating early planning, performance analysis, constructability, controls, and commissioning, you ensure your HVAC system delivers lasting value, energy efficiency, and occupant satisfaction. Thanks for watching this HVAC Master Training video. If you found this breakdown helpful, hit like, subscribe, and stay tuned for our next session, where we'll explore Chapter 2, HVAC Systems and Equipment in detail.